Hello everyone, welcome back to my VLSI Diary. My name is Shivangi Upadhyay and in this video we are going to understand the complete timing path and clock concepts. Till now we have covered multiple important concepts like timing paths, flip-flops, delays, critical paths, clock skew and clock jitter. Now let's bring everything together and understand the complete timing picture of a digital circuit. Now, let's understand that what is timing path. Till now, we have learned about delays like propagation delay and contamination delay. But where do these delays actually exist in a real circuit? Let's understand that using something called a timing path. A timing path represents the path through which data travels inside the digital circuit from one flip-flop to another flip-flop. It is the path of data movement, not the delay itself. Now, let's break this into parts. A timing path has three main components. First is the launch flip-flop. This is where data starts. Data is stored here initially. On clock edge, data is launched. This flip-flop sends the data into the circuit. Second is combinational logic. Next, data passes through combinational logic like AND gates, OR gates, and NOT gates. Here, actual processing happens, and this is where most of the delay occurs. Third is the capture flip-flop. Finally, data reaches the capture flip-flop. This flip-flop captures the data on the next clock edge. Let's see how data flows step by step. Step 1. Clock edge arrives at the launch flip-flop. This is where data is released. Then step 2. Data travels through combinational logic where it experiences delay. Then step 3. Next clock edge arrives. Data is captured by the capture flip-flop. Now here is the most important takeaway. Timing path defines how data moves in digital circuits and all timing analysis in VLSI is based on this path. Propagation delay and contamination delay actually exist inside this combinational logic part. Data starts from one flip-flop, travels through logic, and is captured by another flip-flop. That complete journey is called a timing path. In real chip design, engineers don't look at the single gate. They analyze complete timing path because failure happens across the entire path. In the previous slide, we saw that a timing path starts from one flip-flop and ends at another. So now let's understand the most important element in that path, the flip-flop. First, what exactly is a flip-flop? A flip-flop is a sequential storage element. What does it mean? It can store data and it remembers past values. Unlike combinational logic, which only depends on current input, flip-flop depends on clock plus previous state. A flip-flop stores one bit of data, either 0 or 1. Now let's look at the most important parameter of the flip-flop. First is setup time. Setup time is the minimum time before the clock edge during which data must remain stable. Data should be stable before the clock arrives. Second is hold time. Hold time is the minimum time after the clock edge during which data must remain stable. Data should not change immediately after the clock. Third is clock to Q delay. When the clock edge arrives, output does not change instantly. It takes some time for data to appear at the output. This delay is called clock to Q delay. Now let's see how a flip-flop actually works. First step is data is present at the input T, then clock edge arrives. After a small delay, which is clock Q, output updates. So output changes only on a clock edge, not continuously. This is why flip-flop is important. Also, flip-flop acts as a synchronization element in a digital circuit. They control when data moves. They ensure everything happens in sync with the clock. In timing path, launch flip-flop sends the data and capture flip-flop receives the data. So flip-flop defines the start and end of data movement. Flip-flops stores data, then control timing and synchronize the entire circuit. In real chip design, most timing issues are actually related to flip-flops, like setup violation, hold violation. So understanding flip-flops is extremely important. In the timing part, we saw that data travels from a launch flip-flop to a capture flip-flop. But what happens in between? That is where combinational logic comes into the picture. What is combinational logic? Let's quickly recall it. Combinational logic is made up of gates like AND or NOT, and it does not store any data. Let's first understand its key characteristics. No memory element. Like combinational circuit do not remember past values. They only respond to the current input. Output depends only on input. Whenever input you give, output is calculated immediately based on that input. No past, no storage, only present input matters. Delay behavior. This is very important. Now comes the most important part, delay behavior. Each gate introduces delay. Every logic gate takes some time to produce output. This delay can be propagation delay of that gate. Multiple gate equals to more delay. In real circuits, data does not pass through just one gate. It passes through multiple gates. So delays get added. Total combinational delay is the sum of delays of all gates in the path. In the previous slide, we saw that combinational logic introduces delay. But in a real circuit, there are multiple paths for a data to travel. So the question is, which path actually matters the most? The critical path is the path with the longest delay in the circuit, like longest delay path. Let's look at this diagram. Data starts from launch flip-flop, passes through combinational logic, then reaches to the capture flip-flop. There can be multiple such paths, but the one with the maximum delay is called the critical path. Now you might think, why do we care about the longest path? Because this path takes the maximum time to complete, and the system must wait for this path to finish before the next log page. Critical path determines the maximum operating speed of the system. Your circuit can only run as fast as its slowest path. Clock period must be greater than or equals to the critical path delay. Otherwise, data will not reach in time and the circuit will fail. Exists between two flip-flop. Critical path always starts from one flip-flop and ends at the another flip-flop. It must meet timing constraint. Data must arrive before the next clock edge and satisfy setup and hold condition. Let's say you have three paths. Path 1 is equals to the 5 nanoseconds of delay. Path 2 is having 8 nanoseconds of delay and path 3 is having 10 nanoseconds of delay. Which is the critical path? The 10 nanosecond path because it is the longest path. Remember, combinational delay equals to builds the path. Flip-flop equals to defines starts and end. Together they form the critical path. Critical path is the slowest path in the circuit. In real chip design, engineers focus heavily on reducing the critical path delay, optimize logic, reduce number of stages, use faster cells because reducing this delay directly increases the performance. In the previous slide, we understood the critical path, the longest delay path in the circuit. Now the big question is, how does this delay affect the speed of our system? To answer that, we calculate something called the maximum operating frequency. This tells us how fast the circuit can run safely. Maximum frequency is given by the Fmax equals to 1 divided by critical path delay. Let's understand what this means. Higher the delay, lower the frequency. If delay increases, the circuit takes more time to complete operation. So frequency must decrease. Lower delay equals to higher performance. If delay reduces, circuit can operate faster, so frequency increases. Speed of the circuit is inversely proportional to delay. Let's take a simple example. If a critical path delay equals to 10 nanoseconds, then the maximum frequency is 1 by 10 nanosecond. So 100 megahertz of frequency it will take. So this circuit can run at maximum of 100 megahertz. Now let's connect everything we learned. Flip-flop launches data. Combinational logic adds delay. Critical path equals to longest delay. And that delay decides the maximum frequency. Lower delay means higher speed, higher delay means lower speed. In real chip design, engineers constantly try to reduce critical path delay, optimize logic, then reduce stages, use faster cells. Because reducing delay directly increases its performance. So, in summary, maximum frequency of a circuit is limited by its critical path delay. Your circuit can only run as fast as its lowest path. Till now, we assumed something ideal, that the clock reaches all flip-flops at the same time. But in real circuits, that never happens. Clock skew is the difference in arrival time of same clock signal at different flip-flops. Same clock, different arrival time. Let's understand this with two flip-flops, the launch flip-flop and the capture flip-flop. Clock is distributed to both, but due to wiring delays, routing and load, clock reaches them at slightly different times. Why does clock skew happen? Because in real chip, clock travels through long wires, different paths have different delays, load on each path is different. So clock edges get shifted. Types of clock skew. Now let's understand the two types of clock skew. First is positive clock skew. Captures clock arrives later than launch clock. Capture flip-flop gets clock late. It affects like it gives more time for data to arrive, helps setup timing. Second is negative clock skew. Captures clock arrives earlier than launch clock. Capture flip-flops get clock early. Its effect reduces the time for data to arrive. Can cause setup violation. Clock skew directly affects the timing constraints. Setup time impact is positive skew helps setup timing and negative skew makes setup timing worse. Hold time impact. Positive skew makes hold time worse and negative skew helps hold timing. Clock skew is a trade-off between setup and hold. If skew is too large, it can cause timing violation, setup violation and hold violation, and the circuit may fail. In a timing part, data delay is fixed, but clock arrival also matters. Clock skew changes the effective time available for data. Clock skew shifts the clock and that changes timing margins. In real chip design, engineers carefully control clock skew using clock tree synthesis CTS. Balancing clock path because uncontrolled skew can break the design. In the previous slide, we saw clock skew where clock arrives at different time at different flip-flops. Now let's talk about another real-world problem. What if the clock itself is not stable? Clock jitter is the variation in the timing of clock edges. Clock edge does not occur at the exact same time at every cycle. Normally, we expect clock edge to occur at the perfectly fixed interval, but in reality, each clock edge slightly shifts forward and backward. This small variation is called the jitter. Why does clock jitter happen? Clock jitter occurs due to various real-world factors. First is noise. Electrical noise in the circuit can disturb the clock signal. Second is power supply variation. Fluctuations in the power supply or supply voltage affects the timing of the clock generation. Third is clock source instability. Oscillators and PLLs are not perfectly stable. They introduces small variations in timing. Now let's understand why jitter is dangerous. It reduces timing margin. Like we already have limited time for data to travel. Jitter reduces that available time because we do not know exactly when the next clock edge will arrive. Then it introduces uncertainty. Clock become unpredictable, timing analysis become more difficult. Jitter adds uncertainty to the system. If jitter is too high, data may not arrive on time, can cause setup and hold violations, system may fail randomly. Let's connect everything. Combinational delay equals to fixed, clock skew equals to shift between flip-flops, clock jitter equals to instability in clock itself. All together affects the timing reliability. Clock skew shifts the clock, clock jitter shakes the clock. In real chip, engineers work hard to reduce jitter, use stable clock sources, filter noise, design robust power supply, and because jitter directly affects the reliability of the chip. Till now, we have learned multiple concepts like flip-flops, delays, critical path, clock skew, and jitter. Now let's connect everything together and understand the complete timing picture. In real-time digital circuits, timing is not decided by the one factor. It is the combination of multiple delays and effects. Let's break down all factors involved. First, clock to Q delay. When clock arrives at the launch flip-flop, output does not change instantly. There is a delay called clock to Q delay. Second is combinational delay. Then data travels through combinational logic. Each gate adds delay. Total delay becomes significant. Third is setup time. Before reaching the capture flip-flop, data must be stable for some time. This is called the setup time. Fourth is hold time. Even after the clock is, data should not change immediately. This is called the hold time. Fifth is clock skew. Clock does not arrive at both flip-flops at the same time. This difference is clock skew. It changes available timing margin. Sixth is clock jitter. Clock itself is not perfectly stable. Edges shift slightly. This creates uncertainty. Now imagine all these happening together. Delays in logic, timing requirements of flip-flop, clock shifting, and instability. All these factors combine to decide whether your circuit works correctly or fail. All timing factors together determine circuit's reliability in real chip design. Engineers use a technique called static timing analysis. STA checks all possible timing paths without actually running the circuit and verify if timing constraints are met. If timing is not correct, you may get incorrect outputs, random failure, or complete system crash. In VLSI design, timing is everything. So in this video, we understand the timing path, flip-flops, delays, critical path, maximum frequency, clock skew, and clock jitter. And together they define whether your chip works or fails. Thank you for watching this video. Please like, subscribe the channel. Also share it with your friends in VLSI or embedded domain. Thank you so much.